Alright, so today we'll start with chemical bonding, and it's a pretty important and interesting topic. I would not be writing any notes as the notes are visible, uh, but I would be explaining, and and many students don't like this format, but it's what I have. So let's get started. First of all, before we get into it, let us understand what happens or how on the in the physical world how bonds are formed, right? So what happens is that there is a container, right? There is this container, and there are many molecules here. So let me represent molecule A, molecule A with circles, right? With these circles, and molecule B with this asterisk, right? So when I put these two molecules in a container and they have to form a bond. What happens? So we all know that molecules keep moving around. It means if I take this molecule here, right? There's a molecule here. It will take this path, then it will collide with something. Will take this path and then it'll collide. And then if I raise the temperature, it will have more kinetic energy. So it will start moving around more randomly. So what happens is that when the molecule keeps moving and moving and moving, like a time comes where there's this molecule, it's coming at a very fast speed, and then there is another molecule here, and it dashes the molecule, and a bond forms like this. Maybe it throws away another molecule. Like if there was a molecule of a compound A and then B, and another atom of C comes. Now C has the right speed and the right adjustment. What do I mean by adjustment is that if a compound, or if let's say a target was like this and I had to make a bond with the target, so my molecule will come rushing in and like in this orientation and dash into this compound, right? And then this compound will grasp this molecule and a bond forms. But suppose if my compound was coming like this, right? And they both dash into each other. So there's no way that my left finger can grasp my finger. I'll just hurt myself, right? So in this orientation, the bond does not form. But in this orientation, when the molecule comes like this, the bond forms. So C molecule comes and dashes here, and it replaces the B molecule. All right, it hits away the B molecule. We can visualize and forms a bond with A. So likewise here, what will happen is that this asterisk molecule will move. It'll dash here, it'll dash here, and it will start moving very at a very fast speed. It'll gain momentum or whatever you see, and it will hit this molecule. And somehow it just has the right orientation. It has the right uh, speed, and in those given conditions, some kind of interaction is happening, and then the bond forms. Definition scientifically of a bond is force of attraction between two molecules. Now let us understand why bonds form in the first place, right? What is the why do bonds form? So in nature, there's a simple rule. What's the reason behind the rule? Let's not get into it, uh, because we are not here to be scientists, I guess. But let's have a basic understanding of what the rule of nature is in the context of bonding. If there is a molecule A it always wants to go to a lower state of energy. It always wants to be relaxed, right? It does not want to have lots of energy inside of it. It wants to lose its energy. It wants to go to a lower energy state. Okay, if you had a lots of energy, you'd have to spend it. You'd have to move here and there and spend it, because you can't spend energy by sitting, right? Okay, you do spend energy by sitting, but understand what I'm trying to say. You cannot spend energy by sitting in a place. You have to do some work, and if you cannot do that work, then you cannot spend the energy you have. But if you have no energy, or at least very minimum energy, you can sit in one place easily, and you don't have to do lots of things. Like, for example, many reactions don't happen when the temperature is cold. Many reactions don't happen when the temperature is cold. Temperature is low. Why? Because this molecule has less kinetic energy. It is more stable in its sense, as in it cannot move. It does not have the energy to move. And if the a molecule, okay, let's imagine A looks like this, okay, a rocket ship, or it looks more like a triangle. Let's imagine A is a triangle, and and molecule B is a shape like this. That means it can fit A, all right. But molecule B needs A to move towards it. It needs A to move towards it, right? In a certain speed and a certain orientation. If this is A needs to move in this orientation only to lock into B. Again, to lock into B, a special orientation of A is needed to lock into B. If suppose A was coming like this, they can never lock, because B cannot just randomly expand itself like this. No, B is in this shape only. Alright. So for A to move here to there, it needs some kinetic energy, but there's no temperature, there is no energy to A. So A is stable, A is not making any bonds. But as I raise the temperature, I get to know that A gets lots of kinetic energy. Even B itself gets lots of kinetic energy. And in one container, there are millions and millions of particles of A and B. So they will dash into each other. They will land into the orientation, and they will finally form a bond. So I have this image on Google which can help us visualize. Um, yeah, exactly. So if you look at this, there are millions of molecules, right? There are millions of molecules, and will this red molecule will dash into this molecule, dash, 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 and finally it will hit the yellow molecule in such an orientation, in such a speed that finally the bond can be formed. So those were some basic. I was trying to get the intuition. I was trying to make you have the intuition that how bonds are formed. I think I need to adjust. I think I need to adjust the camera. Great. So let's move on. So okay, I think I need the book. I need the book again. So let's go to this point. Once upon a time, someone discovered the noble gases. Let's take a look of xenon, right? So xenon had done its octet state, and xenon was not reacting with anything. So we were all chill, like okay, so maybe octet and duplet is a governor of bond formation or like stability. That if a atom is in its octet or if an atom is in its duplet, it's more stable, and it does not need to form any new bonds. So we call these inert gases. That means the gases, they don't have the ability to form new things, basically. But then one fine day, a scientist, or I don't know, random nobody came along, came along. and discovered xenon, fluorine, to xenon, fluorine, xenon tetrafluoride, xenon dioxide. And with the discovery of all this, we got to know that duplet and octet are not the only governors of stability, and we need more and more criteria. And I think I just explained it, that stability is a criteria of bond formation. Any compound which has a certain amount of energy X will always try to form another compound which has the energy Y if Y is lower than X. And if it can physically and structurally form a bond, like form a compound like that. Okay, so let me just try and show the notes. If you want, you can write it. You can pause and write it. You can copy this entire thing. I'll get to the explanation. Alright, so take my book again. Let's draw a graph. Okay, and understand bond formation. This point is 0. So there is two molecules. Okay. Oh wait, it's not in the camera. There are two molecules. One has a proton, and in its orbit, there's electron. There is electron. This proton attracts electron. This proton attracts this electron. But these two protons repel each other. These two electrons repel each other. Right? So let's look at a case. Okay, this graph, uh, the y-axis represents potential energy, and the x-axis represents the distance. The x-axis represents the distance. So let's take distance to be infinity. At this point, our distance is infinity. That means the space between the two molecules is infinite. So there will be zero attraction between them because it's so far away that they cannot attract repel each other using their plus minuses, right? Now as I close the distance, they will start attracting each other, right? Now the proton will start attracting the electron, the proton. But some repulsive forces will also be there, right? Some repulsive forces. But in this graph, when I say the distance is reducing, and I reach a point here, that means if I'm able to reduce the distance and there is a loss in potential energy, that means the attractive force are dominating the repulsive force. Now how? What is the reason behind it? Try to visualize. If two atoms are getting closer to each other and they start repelling each other, that means this, okay, if I fix this atom and I'm taking this atom and I'm bringing it closer and closer and closer, and they are strongly repelling each other. As as soon as I let this atom go, it will fly away. It will fly away in the opposite direction. That means when I'm bringing it closer and closer and closer, I'm increasing its potential energy, and it forces this uh, guy here to fly away, right? Uh, so in this graph, when I say that the potential energy is decreasing, is decreasing, is decreasing, is decreasing, is decreasing. That means somewhere they're attracting each other. Somewhere if I leave this atom, it won't fly away. It will actually come closer and closer and closer. So the potential energy is decreasing. And finally, there comes a point where the energy is minimum. That means it's the least energy possible by these two molecules, and that is called the bond formation. That is called the point of bond formation. As we discussed, in nature, atoms, molecules, compounds wants the least energy, so they form a bond here. Now, as I bring those molecules even closer, I'm bringing the protons closer and closer and closer. I'm bringing the moving electron, the electron clouds closer and closer and closer, and hence there is a rise in the potential energy. So now let's go to the more neat notes and try to understand this. So distance is closing, and here the attraction dominates repulsion, and this is the point of bond formation. This is the point of bond formation, and at this distance, I mean, when the two atoms are at this x distance, when the two atoms are at this x distance, the bond forms. The bond forms. So that's why this x distance is called as the bond length. From the initial energy to this point of bond formation, this difference is the bond energy. Now, as we go more closer, repulsion dominates attraction. So there is a rise in potential energy. A very important definition of bond energy: energy released when a bond is formed. Uh, Many people would say that bond energy is the energy minimum energy required to break a bond. No, that is bond dissociation energy. And if you're confused as to why the definition is like this, energy released when a bond is formed, then actually I would like you to explore online. You can ask AI, you can ask Google, but you'll understand it better when you research it yourself. Or else you can ask me in the comments also if you're lazy. Now let's do some questions. I think an important part of the lecture is already finished. Not much of time remains. So which of the following represents the formation of hydrogen H2? Just look at these graphs and try to understand which graph looks most similar to what ours look like. Or let's discuss them one by one, right? If you look at graph A, at this distance, the potential energy is this much. And as the distance closes and closes, there comes a minimum. And then there comes a maximum. Alright. But how is it physically possible for two atoms to have the same amount of energy or have the same amount of attraction repulsion at two different distances? Especially simple. It's a simple atom like H2. Right. So A is not the right option. Likewise, B and D are not right. And finally, we have C. And C somewhat looks like the graph we made also. If this is our point of 0, this is our point of 0, then the graph is very similar to the bond graph which we had drawn in the last page. Let's look at the next question. Which is the following point represents the point of bond formation? Now it's a very easy question. Oh, my setup just fell down. Right. So, which of the following point represents the point of bond formation? So it's very easy. This is a potential energy, right? So we need to look for the least potential energy, and that's point B. Next question. Okay, so this question has two ways to attempt it. Which of the following molecule has the highest thermal stability? So you can draw the structures for each of the following molecules, and you'll figure out that option D has the most amount of bonds. So of course, if it has most amount of bonds, it also has it needs more energy to break. The more bonds you have, the more connections you have, the more power your enemy needs to break you apart. Another way of attempting the question is that we can calculate the oxidation number of the central atom, chlorine, central halogen, whatever. And the highest oxidation number is in option D. So what does that mean is that chlorine is trying to uh, pull, or in another term, when the chlorine has the highest oxidation number amongst the four options, it's it's more like the electrons of chlorine are well distributed uh, in the entire in this structure. In this structure, the electrons of chlorines are well distributed, and hence and hence it's harder to break. Now, if you don't understand how the electrons are well distributed, then you have to understand the topic of oxidation number. And again, that's something you can browse and or go to AI or have some YouTube videos on it. I would actually even like if you have YouTube videos on 3D uh, 3D animation of how bonds are formed. So that is a good concept clearer. Let's quickly finish the next topic. It's not big, it's just classification. So it's entirely notes, you can copy it. Dipole, 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 induced dipole, instantaneous dipole, induced dipole. And all these are van der Waals forces, weak bonds, strong bonds, ionic bonds, covalent bonds. Metallic bond is not in the JE topic syllabus anymore. Uh, let's quickly go over it. I will not take some time. I will get to van der Waals forces. So ionic bonds are the bonds formed by complete transfer of electrons, where there is a develop of positive negative charges in the atoms, right? This Na atom donates one electron to Cl atom, Na plus Cl minus to form Cl, to form NaCl. Here I have written it. The outermost electron in the S subshell, the 3s1, donates its electron to this 3p subshell of chlorine. So the octet is complete, right? Uh, and then here also the octet is complete. So NaCl minus NaCl. Moving on to covalent bonds. These are the bonds formed by the sharing of the electron. This is what we see in the organic compounds, the carbon-carbon compounds. Okay, chlorine says to another chlorine. Both chlorine have 7 right electrons in the outermost shell. So a chlorine meets another chlorine and tells a chlorine that I need one electron from you so I can complete my octet. And another chlorine, this chlorine says that no, I won't give one electron because I myself need one electron to complete my octet. So what they decide is that they will share one electron. They will share one electron, and that's how they form covalent bonds. Remember that whilst you when you represent uh, when you represent ionic bonds, you cannot represent it like this. Na bonds with Cl. No, this is wrong. You have to write Na plus Cl minus. And when you talk about when you talk about covalent bonds, let's say let's say ethane. So C, H, 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 H. Okay, so you can use the bond lines while representing covalent bonds, but not in ionic bonds. These are the weak bonds. Now try to understand van der Waals forces. So we all know that oxygen is a dipole, or it's a polar substance, right? Oxygen is a Because oxygen is more electronegative, so it attracts more electrons to it. There is this one large oxygen molecule, and then there is this hydrogen and hydrogen, and these are babies. These are babies, and oxygen snatches all the electrons. So a partial negative is on the actually a strong negative is on the oxygen. This is a negative sign, and it's not a bond, okay? And there is positive charge on the uh, hydrogen due to the bond distribution. Or if it's not clear, this is our oxygen, this is our hydrogen. Oxygen steals all those electrons, and hydrogen delivers a partial positive. So now if one more water molecule comes, right? Oxygen, hydrogen plus minus. There is a minus charge here and a positive charge on this hydrogen. This is a water molecule 1, water molecule 2, and they both will attract each other because of plus minus distribution. This is also called cohesion in another terms, but it's also called as van der Waals forces. Now, van der Waals forces are weak forces, and if I really increase the strength of the polarity, that means oxygen gets so negative, the hydrogen gets so positive, then they both will attract each other at very high intensity, and breaking them will be cool. So there is one good 3D video by Nuclear Biology, the YouTube channel Nuclear Biology on van der Waals forces. You can watch it. It makes the concept clear. Let's look at hydrogen bonding. It's a very funny thing. Just remember these are the okay. First of all, fluorine, oxygen, nitrogen, and ethine. Sorry, ine, ine. This ine, triple bond carbon, right? And sometimes chlorine shows the phenomena of hydrogen bonding. What is hydrogen bonding? I'll get to it. Okay. Just remember that chlorine shows notable hydrogen bonding in these two examples. This example is called orthochlorophenol, and this example is called chloral hydrate. Okay, just remember these. This is a benzene with hydroxy or alcohol. Hydroxy is alcohol. So phenol, right? So alcohol, and it has a substitute chlorine, and there is a partial bond here, and then there is this kind of spaceship. Okay, with OH here, and chlorine. Now let's get to what hydrogen bonds are, and then it will be very clear. Okay, let's take this space. Suppose I have benzene, and then there is this OH here, and there is this OH here. Now we know that basically, what will happen is that this OH, the O is more negative or more electronegative, so it has a partial negative charge here, and then there's a partial positive charge here, and then there is a partial negative charge here, and then a partial positive charge here. Now can you see some kind of van der Waals forces between this H plus and this O minus? Yes. So they will attract each other, and kind of bond, or let's say attraction, will be established between between these two atoms, right? Or these two molecules of OH and OH, H and O. And this van der Waals forces related to the hydrogen is what we called uh, hydrogen bonding. Now, if you notice these atoms which I have written here, are generally electronegative atoms. Are generally electronegative atoms, and that is why they show the phenomenon of hydrogen bonding. So these are the types of covalent bonds. We'll go through them: odd electron bond, sigma bond, pi bond, delta bond, phi bond, quadruple bond, coordinate bond, and bridge bond. So this is some important data which you have to learn. Okay, let me, yeah. So if you remember the bond potential energy to distance graph, then we can continue discussing it. So during the formation of a bond, during the formation of a bond, when 42 kilojoule per mole energy is released, or more than that, or the two reactants have lost some significant amount of energy, or they have become more stable than what they were, then they form a chemical bond. Now this is where it gets interesting, where between 8 and 42, not exactly 42, but like, of course it's a very big number, but where more than 8 and less than 42 kilojoule per mole energy is released, then it's a hydrogen bond. But how can simple forces of attraction govern the release of energy? Release of energy. Well, that's something you have to browse. If you don't understand anything, then you can ask me in the comments. But uh, it explains a very important thing in organic structures. If you see any organic structure with a hydrogen bond and the same organic structure without the hydrogen bond, although I don't think so it's possible, I don't think so, maybe it should be. But if there are two completely identical organic structures, or let me just draw it. This is a benzene ring with OH here, and then OH. Suppose there's no hydrogen bond between them. And this is the same thing here, but there is OH. There's a hydrogen bond. This structure, this structure, this structure will be more stable than this structure, because it has a hydrogen bond, because some energy is released, right? Because it has gained more stability. So now let's end this lecture by discussing a funny note. Hydrogen bond is actually not a real bond, it's just attraction. So when there is this H fluorine, fluorine has a partial negative, and H plus F minus, there's this bond between them, this hydrogen bond. It's just attraction. Also, these both are okay. Well, let's get to this example first. Hydrogen chlorine, hydrogen chlorine. Again, now why is this? Is this a hydrogen bond? Is chlorine hydrogen? Well, no, it is not a hydrogen bond. Why? I mean, why? It's because I made you remember two examples of hydrogen bonds. One was orthochlorophenol, and other was the spaceship, right? Chloral hydrate. So we only consider those, at least as we are concerned with JEE. If I might be wrong, then please tell me in the comments. But after all, these both are dipoles, right? There is a minus here, there is a plus here. These both are dipoles, right? So these both dipole attract each other with some van der Waals forces, whatever you term it. Let's not get into the theory. My god, my camera fell again. I have written this in my language. इसको डाइपोल बॉन्ड इसलिए नहीं कहते क्योंकि हमने दो कंसिडरेबल केसेस पढ़े हैं फॉर द क्लोरीन क्लोरीन बॉन्ड. Okay, so hydrogen bond Again, these both are dipole dipole, right? Dipole attracts dipole due to the plus minus. So hydrogen bonding is a special case of dipole dipole bond. That ends our lecture one. Uh, it was mostly theory and understanding. There's nothing big in lecture one. Uh, Maybe it seems confusing. Maybe it does not seem confusing. But my suggestion is that you if you have made notes from my notes, I think it's well and good. Um, Maybe after one day, if you look back at it, it'll look very easy. If there is still some conceptual clarity missing from my side, then you can ask me in the comments. I'll be happy to help as much as I can in textual format. Or you can even research on your own. There are many YouTube videos with many good animations. Right. So see you next time.